Hi everyone, my name is Michael Katz. I recently finished my PhD at Northwestern University earlier this year in the spring. In a few weeks, I will be moving to Germany to start my first postdoc at the AEI in Potsdam, which I'm very much looking forward to. Today I will tell you about leveraging accelerator hardware to help us achieve our LISA science goals. I think this is a very underutilized area of gravitational wave science that can really help us move into the future. Today, I'll be talking about a variety of projects in very general terms. I will not be talking about specifics. If you have specific questions, I encourage you to ask about them in the question and answer session, or feel free to email me if that's what you prefer. When I talk about accelerator hardware in this talk, I will be referring to graphics processing units only, GPUs. I do want to point out, though, that there is other accelerator hardware out there, and I really think that we should be looking into all of this accelerator hardware as we move towards the actual launch of the LISA mission in a decade or so. Here I've shown a basic version of the LISA analysis pipeline. We start by building accurate model waveforms. This usually comes from numerical relativity in terms of the binary black hole case, or things like SelfForce calculations for the EMRI case. Once we have those very accurate model waveforms, we then need to create fast and accurate waveforms to use during data analysis. Fast enough means fast for data analysis, and accurate enough means accurate enough for our purposes to have an unbiased and proper statistical analysis. Once we have these waveforms, we put them through the LISA response to understand how the detector itself will transform our readings. We will then evaluate the likelihood, which in its most simplest form is a complex dot product between a noise-weighted data stream and a noise-weighted template. There are some approximations. I'm not going to get into those now, but we are looking at implementing those on GPUs currently. Once our analysis is complete and finished, we will do some form of EM follow-up or multi-messenger astronomy. Now, as I go through this talk, I will show that for basically all these areas, all these colorful blocks, we have used accelerator hardware to improve their performance and to push our science goals forward. The first project that I will talk about is fast and accurate EMRI waveforms. Now, what do I mean by this? What I mean is this is the first time we have fast EMRI waveforms that are fast enough for data analysis while being fully relativistic. The kludge models, which have been previously available, all assume some type of semi-relativistic assumption that really strongly hurts their accuracy and makes them effectively unusable in lots of LISA analysis contexts. Our current model is implemented in the Schwarzschild background with eccentric orbits in a flux-driven trajectory. This is obviously not the Kerr generic orbit second-order self-force trajectory that we will eventually need, but this is a good first stepping stone. And we have built this framework with the knowledge in mind that we will eventually have to expand to higher degree of physics and more intensive calculations. So we have really made this adaptable and flexible. If you want more information, before I keep going, you can check the code at that URL shown there on the bottom left, and our recently submitted paper to the archive shown at the archive number there. Now, I'll tell you about how we can effectively create fast and accurate EMRI waveforms, but as I go through this, I want you to remember that these are effectively separate modules. So if you have an idea for a separate module, you can effectively drop it directly into this framework. You don't have to mess with any of the other pieces, and you'll have EMRI waveforms in no time. So we start with fast trajectories. This is a large stepping adaptive integrator that will resemble something like the near identity transform in the future once we have self-force trajectories. And ultimately, this outputs to us about a 100-point trajectory in terms of the phases as well as the orbital parameters. We then take the orbital parameters and we calculate the amplitudes for all 7,000 plus modes in our Schwarzschild model. We do this in the adiabatic regime, so we do get full Tucholsky modes. We do this with a Roman net, that is a reduced order model artificial neural network. If you want more information on a Roman net, you can see the archive number shown there. But what we effectively do is we take the large amount of Tucholsky amplitudes, the large number of modes we're considering, at all of the P and E values that we are considering, and we project them down into a reduced order basis, and then train a neural network on that reduced order basis. When we are evaluating this in our online analysis, we use the neural network to give us a set of reduced order basis coefficients from where we project onto the full amplitude basis, giving us the amplitudes in all 7,000 plus modes very quickly and efficiently. From there, we do a mode filtering operation. This is done once again only on the 100-point sparse trajectories. This mode filtering operation effectively removes any modes that do not contribute a threshold amount of power to the ultimate waveform, and that is a user-defined quantity. And this usually reduces our modes to about 100 or 200 in the low eccentricity case, up to even 2,000 modes in the high eccentricity case, up at our limits of 0.7. From here, we interpolate all mode amplitude information over time, as well as phases, in a very efficient GPU-implemented parallelized cubic spline fitting method. So if you're interested in a large-scale interpolation of many quantities simultaneously on GPUs, please let me know. I have implemented that in a variety of ways for multiple projects. And finally, we take the interpolation coefficients and other information and we shove it into a summation kernel, which effectively creates the waveform based on this equation shown here on the bottom left. This is by far the bottleneck of the calculation, which I'll talk about in a minute, but I just want to quickly say it's very simple to understand why this is the bottleneck. We have to, at all time points, so millions or more time points, we have to sum all of the modes that we are considering, which can be, like I said, 100 to even 2,000 modes. So in reality, we're looking at a minimum of 100 million or upwards of a billion separate mode calculations that need to be summed up coherently and efficiently. On the top right, you see examples of our fast waveforms compared to the slow waveforms. The fast waveform is in orange, the slow waveform is in blue. This is a slow and accurate waveform that we compare against. Our worst case mismatch across our entire model validity space is 5 times 10 to the minus 4. This occurs in a very specific EMRI. It's our worst case EMRI. It's where we are at our closest separation at our highest eccentricity. That is a separation of 10m, eccentricity of 0.7, as you can see there. The beginning of that waveform, that year-long waveform, is shown in the top panel, and the end is shown in the bottom. As you can see at the top, we have very good agreement, and at the bottom, we have pretty good agreement, but it gets worse. If we remove the last 100,000 points of this trajectory, our waveform mismatch, our last 100,000 seconds of this trajectory, our waveform mismatch improves to about 2 or 3 times 10 to the minus 4, and that is generally where you see the rest of our model maxing out. If we go to lower eccentricity, however, we can see worst case mismatches of less than 10 to the minus 4. On the bottom here, you see the timing for our model, and I'm not going to spend too much time on this, but I just want to point out effectively where this accelerator hardware comes in handy, and that is mainly in the summation kernel itself. So you look at the overall timing going on here, and what we see is that the slow waveform takes on the order of an hour, the fast CPU waveform takes minutes, and the fast GPU waveform takes 100 milliseconds or so, and once again, this is in the worst case scenario where we're considering the most modes. In other words, what I just said, the slow waveform is 36,000 times slower than the GPU fast waveform. Pretty remarkable. Even comparing the fast waveform on the CPU and GPU, we see thousands of times of speed up. And this is once again almost solely due to the summation kernel being so much less on the GPU, because the GPU is just specifically built to handle that type of work. Now, another project we did with GPUs is understanding massive black hole binary parameter estimation. To do this, we implemented the phenom-HM waveform with 6 higher order modes and aligned spins on the GPU, as well as implementing the fast frequency domain least response and a direct noise infused likelihood also in CUDA on the GPU. A direct noise infused likelihood effectively just means that we are doing a direct simplistic dot product with no approximations on a data stream that has noise in it, forcing us to have a large number of Fourier bins, upwards of millions or 10 million points or so, depending on the binary mass. Now, the timing for this calculation is shown here on the left. If we do a Fourier transform of a time domain data stream of 1 year in observation time at a sampling rate of 0.3 hertz, we get the number of points shown by this dashed line. And you can see at this line, which is where we do our calculations for this paper, we are looking at speedups of 400 to upwards of 1,000 times faster than a single CPU core implementation, which is pretty remarkable. But I will say also that this is a bit older now, and I've been working on updating this. That is in process, but I do believe these timings can vastly improve as my GPU knowledge over the past year has vastly improved from when I originally implemented this work. We do this analysis to do parameter estimation tests. We use a parallel tempered MCMC method on the full 11-dimensional parameter space. And one thing, there were a few findings from that, but I think one of the most interesting findings is our ability to see what happens when how the inclination affects our ability to localize sources on the sky. On the bottom here, I'm showing a large binary on the top and a small binary on the bottom, with face-on configuration shown in blue and edge-on configuration shown in orange. I'm not going to get into too much detail about what we expect for the sky locations and whatnot for different masses. If you're interested in that, please see my paper and Sylvain Marsat's paper from a similar time frame that really details this in much more detail. But I will point out that when we have a face-on configuration, we can localize the binaries relatively well, about as well as we expect to be able to, depending on their masses. But when we move towards an edge-on configuration, we effectively lose all of our ability to localize on the sky. And this really has to do with loss of information from the higher order modes, at least in the specific cases that we tested, and effectively losing the secondary polarization in that setup. So hopefully this won't be too big of a deal. This really happens pretty close to the edge-on case, but it was pretty interesting and something that we popped out of our analysis automatically and something that we had to further analyze. Another project we've worked on is accelerating searches for white dwarf binaries. The accelerated search actually has a double meaning here. It means GPU accelerated, as well as including a time derivative of the period in our search. So normally you generally just search periodic sources by searching over the period. But in this case, we have used the GPU, improved upon the old code, and implemented the ability to search over the time derivative of the period, or P dot, in addition to just the period. We did this with the conditional entropy. I'm not going to get into details about how this works right now, but it's effectively a tool to find periodic sources in large-scale surveys. If you're interested, please just look that up. You can get a lot of information from the original release papers. But what I will say is from our analysis, both analytically and numerically, we see that including the P dot can be pretty helpful or necessary for anything under than about 30 minutes in period. Specifically, if you look at this plot down here, which shows effectively a binary that resembles a verification source, where we are only changing its period and maintaining that its P dot is determined by general relativity only, we see the effect of including the P dot in our search versus not including the P dot, and we see that it is extremely important, especially as we get to lower periods. When we get to periods lower than 10 minutes, it becomes hard to even find these binaries. They become undetectable if we search without a P dot. And these are some of the most interesting binaries, some of the most interesting, stronger decay binaries that we really want to look for, and we won't even be able to detect them. If we search with a P dot, not only will we be able to detect these binaries, but we'll be able to strongly detect them with high significance. If you're interested in using this code, which also can be used for general sources, it does not have to be for white dwarf binaries. It can be used in general for periodic sources. You can find it here at our documentation link shown here on the bottom left. If you want more information, here's our paper currently on archive in the review process. If you want more information, please see the archive paper. Now, the last two projects, I'm just going to kind of brush over them as they are in their very early stages of development. But they do kind of involve other areas of the LISA analysis. So the red box is actually highlighted under the zoom window, but I didn't want to remove the zoom window. So this part involves generating very accurate and model waveforms, the first kind of pre-processing step of the LISA analysis. And what we're working on in this realm is accelerating SelfForce calculations. Specifically right now, we're focusing on accelerating the bottleneck, which is homogeneous solutions to the Tucholsky radial equation. To do this, we've implemented in CUDA a Prince-Dormand numerical integrator, originally implemented by Andrew Gloucester and improved upon by myself. And this is, I want to say, generic. It is not particular to this case, so we can use this for other work. If you're interested in that, please let me know. And we've built this in a modular way so that we can expand into generic Kerr orbits in the future as we get this code up and running and checked. And finally, I just want to touch on a newer project which involves evaluating a very accurate time domain response. To do this, we will take numerically generated orbits, which will more strongly resemble what we will see from the LISA spacecraft once we are actually in the midst of the mission. And we will need to take that information and project the gravitational waves in our templates onto the LISA detector to understand its proper response. To do this, we are once again using GPUs. We're trying to get this fast enough to be used directly in data analysis, which we are hopeful of based on initial findings. And I will also add that to do this, we are using Lagrangian interpolation of the time domain waveforms to achieve specific delays from the Solar System Barycenter. If you're interested in Lagrangian interpolation, it is very well suited to GPUs. Please let me know and we can talk about it. So that's it. Thank you very much. I look forward to listening to your questions.